Hi everyone, Architecture and Operating Systems, and we are going to start the second semester of this module. In this semester, we are focusing on computer CPU, function, structure, and also operating systems. What we learn in the first teaching block will help us to understand the stuff and topics in the second semester. In the first teaching block, we learned about binary numbers, how to translate different numeric system into the binary and how to use them to do the operations, arithmetic operations like addition, subtraction, and so on. And also we learned about logical gates, how to create a circuit to be able to do those operations like adder, subtractor. Not only that, we learned other techniques like kernel map and Boolean algebra to optimize them. Now in this semester, we want to see how to use this stuff inside the CPU to do the operation. So this is the question. How do computers do what they do? We want to understand when you want to add two numbers, you know what happens inside the circuit, but what happens inside the computer using different components to do this addition. This is our focus. So computer is a complex system. Complexity means that we've got different components and we've got to put them together in a logical way to be able to undertake different operations. But first of all, we need to learn about computer architecture and computer organization. So first of all, what is computer architecture? Computer architecture refers to those attributes of a system visible to a programmer, or to put in other words, these attributes that have a direct impact on the logical execution of a program. So, as you see here, computer architecture is like a design a house. When you want to design a house, first of all, you need to draw a floor plan, and where is the kitchen, where is the toilet, and where is the different parts of the house. You don't think about the components at that level. So the computer architecture talks about this, that how we've got to use different components, but in the logical way, that to be able to execute a program. So it's like a design a house. But computer organization refers to operational units and their interconnection that realize the architectural operation. It means that it's like building a house by bricks and technology. So first of all, using architecture, you've got to design your house and then use bricks and different technologies and other stuff to build that house. So this is the difference between architecture and organization. In architecture, the logical execution of program is considered. In organization, different components and units we need to put together to actually do the operations. So look guys, as you see, for example, in the mobile phones here, I think it's better to do it like that. In mobile phones, all of them have got same architecture, but we use different components, different organizations in Apple mobiles or Android mobiles. Tablets, they have different architectures, and different models use different brands, use different organizations, but they have same architecture. Same story for the laptops. Most of them use the same architecture, but the components and units are different. Better example, Mercedes. As you see, from this machine, which is very old, to the newest one that we have here, and actually the middle ages of them like this, most of them, actually all of them, have got the same architecture. We need to have wheels, we need to have engine, we need to have gearbox, we need to have different parts that they've got to put them logically to be able to actually to run this machine, run this car. But definitely the organization and components of this one is totally different with this, and totally different with the newest one. But same architecture, but different organization. So This is one of the first computers that we have. And it's quite interesting to let you know and tell you that this machine that is quite new and we use it these days has the same architecture of this very old machine. So today I'm going to tell you what is the architecture of the machine and how it should be. But the organization and technology has changed. For example, the first machine, 1946, that I'll tell you what machine is, it used vacuum tube and the speed is like this, 4,000 operation per second. After that, we are in multiple core CPUs that we can actually operate, and we've got super machine and even cloud machines that they can do loads of operations and in a very higher speed. But all of them have the same architecture. This is about the organization and components. So, computer as a complex system. Computer has got two different parts. Or if you want to study, it's better to focus on two different things. One of them is computer structure, and the other one is computer function. Computer structure is the way in which the components are interrelated. We are talking about how the components work together. Function, the operation of each individual component as a part of the structure. It means that first of all, we need to study the structure and see what are the different components, how to put them together, like memory, like input-output devices, like CPU, ALU, I'll tell you all of them. Different structure, we've got to put them together. But the function is how and what each component does. But I want to start from function first. What are the main functions of our computer? Computer, generally speaking, four main operations and functions. Data processing. Data processing is in this part of the machine. That's our graph here. So it processes the data. So you know that in the adder or subtractor that we discussed in first teaching block, we know how we can use logic gates, put them together, create a circuit to do the operation. So we can process the data here. Storage data. We must be able to store the data. If you want to add two numbers like 4 plus 5, okay, you've got to store the first number and then store the second number, do the operation, and then store the output. So data storage. We've got temporary data storage, we've got long-term data storage, and we need both of them. So data storage is another thing. When you save a file on your machine, actually you are using the storage capacity and facility of your machine. Data movement, internet, data communication. You send the data, you receive the data. The data movement between different parts of the computer. All of them is data movement function of our machines. And at the end, someone should control this machine. It's a control mechanism or control system, which is the most important part of that. When you write a code for your machine using Python, Java, different languages, actually you are helping the machine to control the instructions, the program. So control unit is very important. We will focus on that and discuss it in more details later. Data processing. When you want to process the data, definitely you need to be able to store that. Add two numbers. Get the first data, for example, 2. Get the second data, 4. You've got to store them first. And then, using the control unit there, actually send it to the processor to process it. Give it to the adder subtractor. When you do that, when you do the operation, send it back to the storage because we've got to store that data. Otherwise, we cannot display that on the monitor, for example, or cannot send it to the printer. So we need to have control unit in the middle. Data storage, long-term and short-term, I told you. From the internet, you get the data. You've got to store it. You are getting a website. You are getting the data movement, data storage, long term and short term. When you get the data, you want to add two numbers, you need only short term memory or data storage. But if you want to save it on your hard drive, it's a long term. Again, we need data control unit in the middle. Data movement. You want to send and receive the data. Data movement. Input output devices. For example, scanner, keyboard, monitor, loads of other input output devices. Or we call them, generally speaking, peripheral components. The other external devices that we have, that we use. And also, we've got data communication, internet, all of them happens here in the data movement function of the machine. And again, we must have control in the middle to be able to control all of these operations. Control unit, the most important part that actually handle the data movement, timing, everything between these four components of the machine. Now, we know different functions of machine, components. Generally speaking, the computer structure, it's about the interrelated component. This is the computer. We store the data and we process the data here. We process the data always at this time, actually remind the adder, subtractor. We use that as a processing unit. Storing the data here as well. But we've got loads of peripheral components like keyboard, like a scanner, like printer, communication lines. So as you see, these are the four main components, interrelated components of the machine, and we call it computer structure. We will discuss that in more detail shortly. So, computer structure. What are the main components that we need to have inside the machine? The most important one that we have is called Central Processing Unit, or CPU. CPU actually does whatever we want to do, and it controls the operation of the computer and performs its data processing function. We simply refer it to as processor. So whenever you hear about processor, it means that we are talking about the central processing unit. Then we've got main memory here. Main memory is the memory that we store the data. If you want to get, for example, if you want to add two numbers, 4 and 5, these 4 and 5, in the first place, they need to sit inside the memory because we need to have a place for them, and then send it to the CPU to process the data. Input-output devices is where you write the code. How you write the code? Using the keyboard. Where do you see that? On the screen. When you execute the code, where do you see that? On the screen. Input-output devices are on the top level of computer structure. And also, we need to have a system to communicate the data between these three components. Some mechanism that provides for communication among CPU, main memory, and input-output devices. A common example of system interconnection is by means of a system bus, as you see here, consisting of a number of conducting wires to which all other components attached. So all of these components are attached to this bus that we'll discuss that in 1 or 2 weeks' time, that how send and receive the data between different components. So this is the top level of computer structure. Now we want to focus more on the CPU and see what we have in CPU. Let's look at inside the CPU. So inside the CPU, we've got different components. What are they? One of them is control unit, the most important part. Controls the operation of the CPU and hence the computer. So this is the brain of our machine. How it does that? When you write a code, when you write input X, it sends a signal that everyone should be ready, we are getting a number. So this control unit send signal, by sending the signal, controls different components of the machine. We've got arithmetic and logic unit, ALU, arithmetic and logic unit, performs the computer's data processing function. You know that very well. This is the part that we focus in the first teaching block, because we know that how computer put different logical gates together to do operation. Not only that, we need to have the most efficient circuit. Again, we know how to do that. So this part is what we focused mainly in first teaching block. When using this input output device that you put two numbers like 2, first of all, this ALU converts that to the binary and put it inside the other circuit that it has and do the operation for us. Then we've got registers. Registers or internal memory of our CPU. When you get the data here, it goes first of all sit inside the main memory. Maybe we've got loads of numbers there. But those numbers that we want to use using this system bus, we bring it to the CPU. So we need to have a space to store them. This is called registers. Different type of registers will be discussed later. And then between these four components, we need to have some sort of communication tool. This is called internal bus. Some mechanism that provides for communication among the control unit, ALU, and the register. This is the second level of computer structure. As you see, we can actually study the control unit that we will do, which is about controlling register and decoders, because when we write a code, the computer should understand that and then send the signal. How computer understand that we are adding numbers or subtracting. So these signals inside the control unit will help us to tell the other components like ALU that, look, this is the adder, this is the subtraction. We need to have a memory and we need to have sequencing logic. We will discuss that later on in more details as well. So as you see, these are the three levels of computer structure that we have. Now, you know about the computer structure, different components. I will discuss the architecture shortly a little bit. But what is important to know what happens? Because as I said at the beginning, that the computer architecture from a certain time hasn't changed that much. The stuff that we need to put together to be able to run the programs. But let's see how it was. The first generation of the machine used different organization, different components called vacuum tube. The machine that was made firstly was ENIAC, which stands for the electronic numerical integrator and computer. Designed and constructed at the University of Pennsylvania, was the world's first general-purpose electronic digital computer. The project was a response to US needs during the Second World War. The Army's Ballistic Research Lab, an agency responsible for developing range and trajectory tables for the new weapons, was having difficulty supplying these tables accurately and within a reasonable time frame. So they wanted, in the Second World War, they wanted to have tables for their weapons to actually use them. Without these firing tables, the new weapons and artillery were useless to gunners. That ballistic research lab employed more than 200 people who used desktop calculators, solved the necessary ballistic equation. Preparation of the tables for a single weapon would take one person many hours, even days. So the necessity of having a computer actually was from Second World War. In University of Pennsylvania, they used this vacuum tube and created the first machine. A professor of electronic engineering at the University of Pennsylvania, and with the help of his student, proposed to build a general purpose computer using vacuum tubes for that lab. In 1943, the army accepted the proposal and work began on the ENIAC machine and resulting the first enormous machine that weighed 30 tons, sorry, 1,500 square feet, 18,000 vacuum tubes, and what it does, 5,000 addition per second. So that was the first machine. The first machine wasn't working on the binary system. It was on decimal. It means that they put tens of these vacuum tubes next to each other, and when one of them is on, it shows what number that they wanted to use. And they've got to actually put them together, connect them by the wires manually. So because of that, we call it, that machine worked on manual programming, because manually people and actually people who work there on that machine should manually create the circuit that we use in, for example, and we actually created in logically. So they had to put the wire together from one tube to the other one to be able to program. So this is called manual programming. But these days we don't do manual programming, because what we do, we write a code and the computer interpret that and create the right circuit for that operation. So that was the first machine, but there were some problems with that. The main problem was with manual programming. And another problem was that people should actually write a program and then operate it and create the circuit manually. But someone called Van Neumann, as Germans say, they thought about a new machine, Van Neumann machine or Van Neumann architecture. The Van Neumann machine was started in 1946, but actually they couldn't use that in the Second World War, but that was the initial steps for developing that. The task of entering and altering programs for the ENIAC was extremely tedious. The programming process could be facilitated if the program could be represented in a form suitable for storing in the memory alongside the data. So the idea was this, which is very important. That was a stored program concept. It means that in the same time, not only we should be able to store the data on the machine, but also we should find a way to store the program on the machine as well. In that case, it's easier for us to do the operation. The idea known as a stored program concept is usually attributed to the ENIAC designer, most notably the mathematician John van Neumann, who was a consultant on the ENIAC project. So Van Neumann wanted to solve the problem of storing the program and the data both on the memory. So that was the idea of Van Neumann architecture. So what he did, actually he created the first machine called IAS, Institute of Advanced Study computer, and which took a couple of years, 6 years to build that machine. This machine works based on binary numbers. The ENIAC was on decimal system, but Van Neumann was on a binary system. And he proposed architecture for that. This architecture, or IAS, or Van Neumann architecture, is something that these days all the machines are work based on that. So this is the structure of this machine. A main memory which stores both program or instructions and the data. We have this main memory to store both data and programs. Because of that, this is called stored program concept. Store both of them. It means that when you write a code, for example, x equal y plus z, the machine will translate that as an instruction and put it inside the memory. Also, we've got the CPU, central processing unit. In the CPU, we've got the program, control program unit, CC, and we've got ALU, arithmetic logic unit. And also we've got input and output devices. So this is the main structure of the Van Neumann machine that we will discuss in more details later. But one thing about Van Neumann or IAS computer, about the memory. The memory, because I said that it's a stored program concept, so we need to have a memory to be able to store both numbers, data, and also the instruction. So this memory, this machine memory, has had 1,000 locations from 0 till 999. We've got two types of words. Word is actually the length of the memory that we used, that they used actually. The number word, which the first bit shows the sign of the number and the rest for the magnitude. So it used sign magnitude. This is for storing the number. What about the program or instruction? They use another word called instruction word, and they're using two parts, 20 bits together, 20 bits together, right instruction and left instruction. But what it means, they use 8 bits for the opcode and 12 bits for the address, for example, for the left instruction. What it means, opcodes, it has some code for example, if you want to add two numbers, for addition, you store 1 here. If you want to subtract, you store 1 0. It means that the opcodes are the codes that they use to actually tell computer what to do, to send a signal based on that, and they could save it on the memory. For example, you want to add two numbers. One of them is in the first row and the other one in the second row. First and second row. So first of all, you say that, okay, what you need to do, go and read. For example, 1 is reading a number. Read the first word. The second instruction, read the first row. So you've got to give the address here. Then second instruction is to add. For example, adding, the code for adding is 2. Adding the second number, so you give the address. So as you see here, you could address the memory and tell computer what to do using this opcode. We will discuss that definitely in more details when we discuss fetch execute cycle. But what is the most important thing, that Van Neumann or in IAS computer, they thought about store the data and instruction, both of them on the machine, in this way. Storing the data using signed binary, we know how it works, and then store the instruction using binary numbers. We will discuss that later in more details. So this is the end of the first lecture for this part. This is the reference of already scanned and put it on the Moodle page, but also you can find this book on the resources tab on the Moodle page. Thank you very much. There are a bunch of questions for the practical session that you need to answer the questions based on the stuff that we discussed, and upload it to a Google form that I've already put it on the Moodle